this video, we'll look at applying the double angle identities while utilizing, again, triangles. So remember, anytime that you're given this information, the sine of theta in this case equals to 4/5, and theta is in the second quadrant. This second statement is not null and void. It's so important that we actually register where that is. So when I go ahead and I build sine of theta equals to 4/5, I'm going to build it in the second quadrant to be able to evaluate the sine of 2 theta. Now you might be thinking, well, why do I even need this information? Well, if we look at the sine of 2 theta, keep in mind, it's not just multiplying 2 by 4/5. We can't replace the sine of theta with the sine of 2 theta and think that the 2 is sitting outside. This 2 sine of theta is nowhere equal to sine of 2 theta. These are not the same thing. Do not assume that you can replace the sine of theta in here because, again, I can't just pull the 2 out. That mathematically doesn't work. So first thing I have to do is I got to figure out how this is important. Well, I know the sine of 2 theta has a double angle identity such that it's equal to 2 times the sine of x times the cosine of x. So this does equal to 2 sine of theta times the cosine of theta. That's going to be true. And if that's the case, and this side here equals to the 2 sine of theta cosine of theta, it makes sense that I now need to know what my cosine of theta is going to be in this problem. So off to the side here, I'm going to go ahead and build this sine of theta equaling to 4/5 in that second quadrant. So it's going to go ahead and spit out this way. There's theta. The right triangle is always dropped back perpendicular to the x-axis. My sine is 4/5. And because this is, again, one of those basic examples, that missing side is 3. Don't forget that this is in the second quadrant, so that value has to be negative. So now that I know what cosine of theta is going to be based on this triangle, cosine of theta is -3/5, I can then finally evaluate what the sine of 2 theta is. 2 times my sine is 4/5 times my cosine is -3/5, and therefore I'm going to have 4 times -3 is 12, times 2 is -24, divided by 25, and that evaluates that piece. Now, for the rest of the examples in this case, I can simply use this information here to evaluate each of these pieces. Let me go ahead and look at the double angle identities for cosine of 2x, in this case cosine of 2 theta. If I look at all three of these cases, again, it can be equal to this one, it can be equal to this one, or it can be equal to this one. I'm going to select whichever one makes my life the easiest. And it's not going to be this first case. And the reason why it's not going to be the first case is because what if I made a mistake on this? Yeah, then this problem may be wrong. But if I make a mistake on this and I use it here as well, then this one's also going to be wrong. Let me save myself the trouble. And if I'm looking for the cosine of 2 theta, I can use this example right here in the middle, 1 minus 2 sine squared of x. If I use that one, then I'm going to use the sine of theta as 4/5 and avoid any other issues with the cosine. So this is equal to, by the double angle identity of cosine, 1 minus 2 sine squared of theta. Now, you might be having an issue with the fact that it's now sine squared of theta, but don't be afraid of that. Just remember that the sine squared of anything is the same as this being written. So now I can replace sine of theta with 4/5 and square that number. So I get 1 minus 2 times 4/5 squared. That's going to be 1 minus 4 squared is 16 times 2 is 32. So 32 all divided by 5 squared is 25. I can go ahead and change this to be 25 over 25, and I'll be left with a -7 divided by 25 is the final answer for that. Now, if you had used this first case or the last case, and you utilized this value, and this value was correct, then you would get the exact same number. It wouldn't matter. The only reason why I used this example here, this particular identity, is because I wanted to avoid any other possible errors that I could have made in steps to getting to this. I know that this is what they gave me. This is what's true. If I convert this to this example, then everything else is just a matter of arithmetic. So the last one we're looking at is tangent of 2 theta. Now again, we can go back to tearing it apart and using both of these separately, but I think I'm just going to go ahead and pick one of these basic examples. I like this one right here simply because it doesn't have multiple trigonometric identities or multiple trigonometric functions. I could use cotangent, but cotangent is one of those more reciprocal identities or quotient identities that are more complicated to work with. And this one has both tangent and cotangent. Again, leaving me a chance of making bigger mistakes. So all I'm going to do here is I'm going to go ahead and find the tangent of theta in this particular example. Tangent of theta is opposite over adjacent, so 4 over -3, which can be written as -4/3 if you're so inclined. And I'm going to go ahead and use this piece right here. Again, I could find cotangent and use this instead, or use this one instead, but I'm going to stick to the basic one that I can identify. So this is going to be equal to 2 times the tangent of theta divided by 1 minus tangent squared theta, remembering that I'm squaring the entirety of tangent of theta. Again, this is the only time that the squared is not inside the tangent, it's actually on the whole tangent. We just write it in here because it saves space and it saves time, and it doesn't look like it's the theta that's squared. Again, if the theta was squared, it'd be an entirely different story. But in this case, I'm looking at 2. My tangent of theta is negative 4/3 divided by 1 minus, and then it's negative 4/3 again, but that whole thing is squared because that whole negative 4/3 is replacing my tangent of theta, and my tangent of theta is what's actually squared. So very carefully, I'm going to have negative 8 divided by 3. Notice how I'm writing it with the side division instead. And this one here, I'm going to square that, so it's still going to be 1 minus, and then it's going to be positive 16 over 9. If I want to go ahead and combine terms as best as possible and simplify as best as possible, I'm going to change this to 9 over 9, giving me negative 8 over 3. Divided by 9 over 9 minus 16 over 9 is simply going to condense this down to be a 7, so negative 7 over 9. If I keep flip change these fractions, the negatives are going to cancel out, and I'll be left with 8 over 3 times 9 over 7. I'm going to be able to cancel out the 3 and the 9, leaving me with 8 times 3, 24 over 7. And that is the final answer for the tangent of 2 theta, the cosine of 2 theta, and the sine of 2 theta, given simply the sine of theta is equal to this. Once we have what quadrant it is and what the value is, we don't need anything else other than to build a triangle if we're missing specific trigonometric values. But that's how you, again, utilize triangles to evaluate double angle identities given a single trigonometric